we're going to learn about 7.8 improper integrals. Okay, so what are these things about? This is where you have an integral which either goes from some number all the way to positive infinity, or some number to negative infinity, or from negative infinity to positive infinity. That's improper integral of type 1. Or when you have an integral of a function that has a vertical asymptote. Okay, and you have to try and make sense of what that means. So far we've been talking about integration when we have functions that are continuous or have just finitely many jump discontinuities. Now we have to try and understand more generally what an integral is when we have either an infinite domain or a function that has a vertical asymptote, and we want to integrate all the way up to the vertical asymptote. So we start with integrals of type 1. So consider the following integral. Okay, let's visualize what this means. So at 1, x is 1, so this function 1 over x squared is 1, right? And it's obviously decreasing as x increases. Yeah? Like this. So what this thing is asking us is, what is the area underneath the graph of 1 over x squared from 1 to infinity, all the way to infinity, right? And that is a meaningful quantity. We can understand what that means. That's the area underneath this graph thing going off forever, right? Yeah? Now, what we can't do is just use the fundamental theorem of calculus and then plug in infinity into the endpoints, because that has no meaning. Infinity is not a number. And I'll show you lots of examples where if you just think of infinity as a number, you just get nonsense out. So we have to make precise what we mean by this quantity right here, right? Our only way to calculate definite integrals, not our only way, but our best way to calculate it is the fundamental theorem of calculus and taking the antiderivative and just doing capital F of B minus capital F of A. We can't do that so simply here because infinity, again, is not a number we can just plug into a function. So this is how we're going to make sense of this quantity. And it's a very natural way. We're going to say, okay, this thing is meant to represent the entire area underneath the graph of this function from 1 to infinity. If we just took the area from 1 to, say, capital R, like this stuff we can for sure calculate, right? We can just plug that into the antiderivative of this thing. So if we did the integral from 1 to capital R, 1 over x squared dx, and the antiderivative is this thing, right? So what do we get? We are going to get, minus 1. No, we're not. We're going to get minus 1 over r minus 1, which is just the same as plus 1. Yeah? Which is a totally meaningful thing. Yeah? Cool. And if we want to find the area of this thing for a bigger number, right? Let's call that bigger number, say, S. So this thing here is S. Then that's the area of all of this stuff, all the way up to S. Again, we can just figure it out. We can just put in S into this thing. Huh? Yeah, that stuff is easy. Yeah? And what are we actually looking for? We're looking for the entire area underneath the graph of 1 over x squared from 1 to infinity. And that thing will always be less than the integral from 1 to any big number, right? But if, as we let this big number, s, get bigger and bigger and bigger, we get some answer which is consistent, which is tending towards some consistent thing, yeah? Then it would be reasonable for us to say that the meaning of this is the limit of the integral from 1 to s as s goes all the way off to infinity in the limit. That's a meaningful thing, right? Yeah? And that's the way we can actually define what this quantity is. Define what this quantity is and actually have a way to calculate it. Yeah? Cool. So that is what we're going to do. We will define this thing to be equal to the limit as r goes to infinity of the integral from 1 to r of 1 over x squared dx. Yeah? And that seems right. That seems like the right thing. Yeah? This quantity will always be less than the total area from 1 to infinity. But if, as r goes towards infinity, we tend towards some quantity, some limit, some finite number, then that thing, that finite number, is reasonable for what this thing is. Yeah? You see what I mean? Yeah? Give me a thumbs up if that seems reasonable to you. Cool. All right. So we've already done this calculation, right? We know this is this, so that's just the limit as r goes to infinity of minus 1 over r plus 1. And then this limit is easy, and as r goes to infinity, minus 1 over r goes to 0, so this limit is 1. Yeah? So we've now learned the total area underneath the graph from 1 to infinity of 1 over x squared is 1. Yeah? Cool. Yeah? And you might think, okay, well, no big deal. Well, this doesn't have to be this way. So, for example, consider this. If we do the integral from 1 to infinity of 1 over x dx, it looks kind of similar, right? It starts at the same place, right? And what's the difference? Well, as x gets bigger and bigger, right, x squared is bigger than x, so 1 over x squared is smaller than 1 over x. Yeah? So this guy, which is 1 over x squared, is going to lie underneath this guy, which is 1 over x, right? But they look really similar, right? You plot them on a computer, they look really similar graphs, right? Yeah. But let's try and figure out what the area underneath the graph of 1 over x is. Let's see what happens. Well, we have to calculate it by doing this thing, by taking the limit from 1 to r as r goes to infinity, right? Or I should say the limit of the integral of 1 to r. And again, this stuff is something we can calculate. It's the limit as r goes to infinity. The antiderivative is just log of x, or log of absolute value of x. And then what is this? This is log of r minus log of 1, which is 0. Oops, so that's just log of r. Yeah? Well, I forgot the limit signs. So this is the limit as r goes to infinity. And what's this? What's the limit as r goes to infinity of log of r? Okay, we need to do some recap maybe on elementary functions. So log does this. Log does this. It's the slowest growing elementary function that we have, right? But it goes to infinity as r goes to infinity. Yeah? Because what is log? Log is the inverse of e to the x. Okay, this is all recap. Log is the inverse of e to the x, right? So you people are very happy that e to the x goes to infinity as x goes to infinity, right? Yeah. So log is unwrapping it, but that means that log has to send infinity to infinity as well, right? Yeah. There's no way we can have an inverse unless it also grew to infinity. But it's going to grow to infinity incredibly slowly because it's unwrapping the action of e to the x, which is going incredibly fast to infinity, right? So the graph of log is this. As r goes to infinity, log of r goes to infinity. Yeah? Is this coming back to you? Yeah? Okay. So the faster you people get comfortable with elementary functions, the more time you will save, because we're gonna be playing with these guys all the time. We're gonna be talking about about all of these guys, log, exponential, trig functions, arctrig. We're gonna have these players involved in this story constantly. Yeah? And what I'm going to emphasize to you is to visualize what we're doing all the time, which means having the graph of these functions in your head. Okay, so my students from previous Calc 1 have heard me say this dozens of times. Those of you who are new to my class, you're going to hear me say this many times. Please, if I mention an elementary function and I talk about its graph and it's not familiar to you, make a note of that and then get comfortable with that graph. So we've learned graph sketching. That's the best way to do it. You could also just type it into computer, but that's not nearly as good as just figuring out its properties from how you know how to do graph sketching. Huh? So make sure you're happy with log if you're not happy with log, and every other elementary function. It'll save you so much time going forward. Yeah? All right, so we have log, and as r goes to infinity, log of r is going to infinity, so this is infinity. So what does this mean? It means that this thing is actually, even though it looks very similar, has infinite area underneath its graph. Yeah, so it's going down to 0, yeah? But it's not going down to 0 fast enough so that the area underneath the graph from 1 to infinity is finite. It's actually infinite. Yeah? So even though these functions 1 over x and 1 over x squared look kind of similar, behave kind of similarly, they've got radically different behavior in terms of how much area there is underneath the graphs from 1 to infinity. And that's going to be a key point going forward, because we're going to have many functions. We're going to consider the integral from 1 to infinity, or from 0 to minus infinity, or from minus infinity to infinity. And we're going to try and figure out if that thing has a meaningful finite answer, or if it doesn't. If it doesn't, we say it diverges. Okay? If it does, we say it converges. Yeah? And the game to understand, or the thing to understand, is how quickly is this going down to 0? And if it's going down to 0 fast enough, like 1 over x squared, then the area underneath the graph will be finite. And if it's not going down to 0 fast enough, then it won't be. Okay? So we've learned that 1 over x squared is going to 0 fast enough, and 1 over x is not. Yeah? Yeah? And now, in all future questions, that's the first thing we're going to ask. We're going to ask, do we believe this function is going down to 0 fast enough so that the answer is finite? Yeah? And then we'll try and do some calculations and see if that conforms with whatever intuition, whatever picture we have based on answering that question. Okay. Let me erase the board and do some more of this. Let's consider this question more generally. So we've learned that if we have 1 over x, it is not going to 0 fast enough. 1 over x squared is going to 0 fast enough. Yeah? Let's consider 1 over x to the p. So consider 1 over x to the p for p bigger than 1. Let's see what happens with this. Yeah? As before, we're going to draw a picture. At 1, it's 1, right? It is, of course, decreasing. And our question is it decreasing fast enough? Or for what p will it be decreasing fast enough? Okay, and we can just do the calculation. So we integrate from 1 to r of 1 over x to the p, and that is to 1 x to the 1 minus p over 1 minus p. This, and this is 1 over 1 minus p of r to the minus p minus 1, like this. And since p is bigger than 1, then 1 minus p is negative. So let's write this as p minus 1, and then put the minus through like this. So it's 1 minus r to the 1 minus p. And again, since p is bigger than 1, this thing is negative, so we can actually just write this as 1 over r to the p minus 1. Like this. Yeah? Again, p is bigger than 1, so this is a positive quantity, this on the bottom is a positive quantity. Yeah? So as r tends to infinity, this thing is just equal to 1 over p minus 1. Yeah? Which is finite. Which makes sense. Yeah? Cool. And when p is equal to 2, then it's 2 minus 1, which is 1 over 1. We recover the result we had before. Yeah? And as p gets closer and closer to 1, then p minus 1 gets to be smaller and smaller. So 1 over a very, very small number is a very big number. So as p gets close to 1, this thing blows up, which is what we'd expect, because we know when p is actually equal to 1, it's infinity. So we'd expect as we push p closer and closer, or down closer and closer to 1, then the graph is getting bigger, right? Because of the following. So for x bigger than 1, right? X to the p is bigger than x, which is the same as saying that 1 over x is bigger than 1 over x to the p. Yeah? So our 1 over x is on top of this guy. Yeah? Yeah? But as p gets closer and closer to 1, then it's less and less on top of this guy. It's getting bigger and bigger and bigger. See what I mean? Give me a thumbs up if you're with me here. Okay, cool. So what we've learned is that 1 over x is the cutoff. So if it's going down to 0, like 1 over x, it will not converge. It has infinite area underneath this graph. And if it's going to 0 just a little bit faster, like 1 over x to the p, where p is bigger than 1, then it will converge. So it just needs to get a little bit under 1 over x, and it will actually converge. Okay, and we're going to keep that in mind going forward, because we're going to look at these various examples, and the first thing we'll ask ourselves is, do we believe it's actually going to converge? Yeah? And if we believe it's going to converge, well, whether we believe it's going to converge or not, we're going to do the calculation. And then if the calculation conforms with what we believe based on this quick analysis, yeah, then we're happy. And if it doesn't, then we think, okay, we probably made an algebraic calculation. In other words, we're going to think about the pictures first of all, and then we'll do the calculations, and then we'll check back with the pictures to make sure it's consistent. Okay? We're not going to just do a calculation and not think about what it means. That is what I'm going to try and get you out of. We're going to think about what stuff means all the time. Okay? Let's do an example. Okay, this is example 3. What about the integral from minus infinity to infinity of 1 over 1 plus x squared dx? Okay, solution. Firstly, we notice that this is a symmetrical function, right? If we have minus x or x, it doesn't notice, yeah? It doesn't notice. So this thing, let's call this thing star, is the same as just doing twice the integral from 0 to 1, 1 over 1 plus x squared dx. Yeah? Everybody with me? So let's look at what the graph looks like, right? So it starts off when x equals 0 at 1, and then it's decreasing. Yeah, it's decreasing like this. Yeah? But what about when we go in the negative direction? Well, if we put in 1 over 1 plus minus x squared, yeah, then that's the same as 1 over 1 plus x squared. Yeah? So when we have x here, if minus x is here, we're going to have exactly the same value. It's what we call an even function. Yeah? So we have exactly the same thing happening, the mirror image across the y-axis happening like this. Yeah? So the area on this side from 0 to infinity is exactly the same as the area from 0 to minus infinity. So the total area from minus infinity to infinity, is just perfect. Thank you again for the question. All right, everybody with me? Because I made a typo. Thank you. Perfect. All right, look at this. Tell me if you believe that this thing will converge. Yeah, 1 over x is where it doesn't work, and if it goes a little bit faster, like 1 over x to the p for some p bigger than 1, then it will converge. And exactly as this guy says, this thing is going down to 0 like 1 over x squared, right? For very large x, then this 1 plus is not making any real difference, yeah? And in fact, since it's a 1 plus, we actually have that 1 over 1 plus x squared is less than 1 over x squared, yeah? Yeah? At least for all, actually for all x, but certainly for all x bigger than 1, yeah? So we know as we integrate from 1 to infinity, 1 over x squared has got finite area, and this guy lives underneath it, yeah? This guy lives underneath it. You see what I mean? Yeah? So it lives underneath it, then for sure this guy from 1 to infinity has finite area. Yeah? And then this guy from 0 to 1, it's just finite, right? Because this thing is, this expression 1 over 1 plus x squared is always less than 1. Yeah? So this part right here, this part right here is not going to make it infinity. Yeah? Everybody with me? Cool. All right. So just by the fact that we have this power x squared, we believe it's going to converge. We believe it's going to converge. What if we instead had something like this? What if we were integrating from, say, 2 to infinity, 1 over x squared minus 1 dx? What do you think? Would that converge? Are indeed going to have greater values. That's true, but not much greater values, because x squared minus 1 is bigger than x squared, yeah, which means that the other way around, is less than x squared, like this, which means that 1 over x squared is less than 1 over x squared minus 1, so it's living above the graph of 1 over x squared. But for very large x, this thing, x squared minus 1, is an awful lot like just x squared. Yeah? It's an awful lot like x squared. So it will turn out that this thing actually will converge, because it's still, in terms of its power, going down to 0 like 1 over x squared. Does that seem reasonable for you people? Yeah. So what we're really looking for is the power of the decrease. The power of the decrease. And if the power is bigger than 1, then we expect it to actually converge. And if it's equal to 1 or it's less than 1, it's between 0 and 1, then for sure it won't. Yeah? That's what we're looking for. That is going to be our intuition. Okay? But we'll do the calculation. We'll do the calculation. First we get the intuition, then we do the calculation. So let me try and erase this. So, as you people told me, you expect this thing to converge. And how we're going to do this, we're going to take the limit as r goes to infinity of 0 to r, 1 over 1 plus x squared, right? That's the limit as r goes to infinity. And what is this quantity here? What's the antiderivative of 1 over 1 plus x? Arctan, good. This is arctan. Oops. Yeah, like this. So then this is the limit as r goes to infinity of arctan of r minus arctan of, not 1, 0, 0. Okay, show me with your finger what the graph of arctan looks like. Show me with your finger what the graph of arctan looks like. Okay. Looks like many of you have it. So, graph of arctan looks like this. Right? It has a horizontal asymptote at pi over 2 and at minus pi over 2, like this, right? So in particular, the limit as arctan, well, it's exactly the statement of having a horizontal limit, horizontal asymptote. This thing is exactly pi over 2, right? Because it has a horizontal asymptote. Yeah? And this thing is just going to be 0, right? Arctan of 0 is 0. Yeah? So then we just have pi over 2. Yeah? Everybody happy? Cool. But this thing is just half of what we know, because the actual thing was the integral from minus infinity to infinity. So the actual answer is that star is just equal to pi, because it is twice this. All right, let's do another one. Improper integrals of type 1. When we have the integral from any number a to infinity of some function f of x dx, that means the limit as capital R tends to infinity of a to r f of x dx. That's what it means. That's how we'll calculate it. And when we have the integral, say, from minus infinity to some other number b, or the same number, doesn't matter, of, say, a function g of x dx, then what does that mean? Well, it's defined analogously. Now we're going towards minus infinity, and this is just a limit as, say, s goes to minus infinity of s to b g of x dx. It's exactly the same game, right? Except we're going to the left, except instead of to the right. And then c, if we have something like this, minus infinity to infinity, let's say h of x dx, this is equal to the integral from a to infinity h of x dx plus the integral from minus infinity to a of h of x dx, if those two integrals converge. If those integrals converge, and that's true for any a. So we can pick any number a along the real line. Suppose a is here, and then we consider the integral from a to infinity, and then the integral from a to minus infinity. Okay, and those things we know what it means, because that's this case and this case. Yeah, and if both of those things converge, then we define the integral from minus infinity to infinity to be the sum of this guy, the stuff from a to infinity, plus the stuff of the other guy from minus infinity to a. Yeah? And from the pictures, that makes sense, right? That's a reasonable way to define the integral from minus infinity to infinity, right? And you can also see from the pictures that it doesn't matter what a we choose. If there is some a for which we can do this, for which we'll have this guy and this guy converges, then we can define it like this. Do you see what I mean? Does that seem reasonable? Yeah? Cool. So this is this, and this is this. And if both of those things make sense, then this thing is the integral from minus infinity to infinity. So this is the graph of h. Cool. So type 2 improper integrals. These are harder, because this is when we have a function with a vertical asymptote. So here is 0. Classic example is, say, 1 over x. So if we take 1 over x, this time from 1 to 0, we know what the graph looks like, right? It looks like this. That's 1 over x. Yeah? And we can ask ourselves, does this have any meaning? So is there a meaning to this? The integral from 0 to 1 of 1 over x. Yeah? Does this mean anything? Yeah? And again, we can't just take the antiderivative and plug in the numbers because it makes no sense, right? Because the antiderivative is log. A log of 0 is infinity. We can't just, evaluate it there. We can only apply the fundamental theorem of calculus for some continuous function, yeah? So we have to try and make sense of this. We have to give a meaning to this, yeah? And the way we're going to do it is conceptually analogous to the way we did it before. We're going to consider the area underneath the graph, not from 0 to 1, but from 0 to some small quantity, let's say delta. Yeah? Well, actually, let's call it not delta, let's call it A. And then this thing, so long as A is bigger than 0, this thing is meaningful. This thing is meaningful because the function is continuous from A to 1. Yeah? So this blue stuff I've just drawn, this is an area. This is the area which makes sense, right? And as A increases, we're going to get more and more of the area underneath the graph of 1 over x. Yeah? And the meaning we're going to give to this thing is going to be the limit as we let A tends towards 0. Right? We're going to kind of exhaust the area we're interested in by these areas that are inside it. Yeah? And if we can do this and then get a limit out in the end, that will be what we define this thing to be. So conceptually, it's analogous to when we did the improper integrals of type 1, right? Because we exhausted the area from 1 to infinity by just taking the integral from 1 to capital R as R got bigger and bigger and bigger, right? We just filled it up. We're going to do the same thing here. Yeah? We're going to do the same thing here. Yeah? Cool. So let's see if this makes sense. So if we take this limit, the limit as A goes to 0 of the integral from A to 1 over x dx. What's this? This is the limit as A tends to 0 of 1 to A log absolute value of A, like this, right? So this is limit of A goes to 0 of log of 1 minus log of A. Yeah? Log of 1 is 0, so that's the limit as A goes to infinity of minus log of A. Not infinity. Damn. Sorry. 0, 0, 0. Yeah? That's what the picture tells us, right? So what we're doing is describing in the language of maths what this picture is. Yeah? All right, cool. Tell me about this limit. What's this limit? Right, so the graph of log is like this, right? At 1 it's 0, it increases, but from 1 down to 0, it's negative like this, right? And as we go towards 0, it goes towards negative infinity. Yeah? That's the graph of log. Yeah? Coming back? Okay. This is the graph of log. So this thing in particular is infinity, right? Because the limit as A goes to 0 of log of A is minus infinity, so minus that is infinity. Yeah? Cool. So what does it tell us? It tells us that we have infinite area underneath the graph of 1 over x from 0 to 1. We have infinite area underneath the graph of 1 over x from 0 to 1. Yeah? So this guy, 1 over x, is blowing up to infinity so fast we can put infinite area underneath the graph just over this little interval 0 to 1. Yeah? It's kind of surprising, right? You might not expect that, but it's true. It's the case. We've just seen it. We've just shown it. Yeah? Cool. All right. So our problem is that 1 over x blows up too fast. 1 over x is blowing up too fast for there to be finite area. Yeah? So let's see if when we have something that blows up less fast, if the integral will actually be finite. Yeah? So what's an elementary function that would blow up less fast? What if we consider one over square root of x? Consider that. Yeah? So notice, and this is a key point, if x is between 0 and 1, then the square root of x is bigger than x, right? Yeah? Because, for example, if you have a quarter, yeah, and you take the square root of a quarter, you want to find what number multiplied by itself gives a quarter. Well, that number is a half, right? Yeah? So the square root of a quarter is a half. It's bigger than what it is. You also know what the graph of square root looks like, right? The graph of square root looks like this. Yeah? And this is the graph of just y equals x. So it's bigger than itself. Square root of some number is bigger than the number itself. Yeah? Yeah? The number itself is here, and this is the square root. This is the graph of square root of x. Yeah? So, if we have x between 0 and 1, square root of x is bigger than 1 over x. So that's the same as saying that 1 over x is bigger than 1 over square root of x. Yeah? So as x tends towards 0, then for sure this is blowing up, but it's not blowing up as fast as 1 over x. It's not blowing up as fast as 1 over x. Yeah? Cool. So let's see what happens. It might have a chance to be finite because it is not blowing up as fast. So if we try and plot this guy, it is underneath, right? It's underneath. It's still blowing up, but it's underneath. Yeah? So it might be that this thing is such that the area underneath it is finite, even though 1 over x, it's not. Let me try and put it up here. I'm running out of time. All right, let me do this, and then all of you who need to leave can just leave. So let's look at this. We take the limit as a goes to 0 of the integral from a to 1 of 1 over the square root of x dx. That is the limit as a goes to 0 of, what is this thing? This is the same as x to the minus a half, right? And then what do we get as an antiderivative? If we take x to a half and we differentiate, we get a half x to the minus a half, which isn't quite right. So if we put a 2 here, then differentiating this thing would give us this thing. So this is what we want. And this is a to 1. So this is equal to 2, the limit as a goes to infinity of 1 minus square root of a, which is just equal to 2, which is indeed finite. It makes, not infinity, damn it, to 0, which is just equal to 2, which is a finite number. So what we've learned is that this guy is blowing up sufficiently slowly so that the area underneath the graph is actually finite. Yeah? So sometimes we have a vertical asymptote which is blowing up sufficiently slowly so that the area underneath it will be finite. Yeah? And sometimes it'll be blowing up too fast so that it won't. And let's try and find the cutoff point. Okay, let's finish with this. Let's try and find what happens if we just take a general p. Okay, and p will be between 0 and 1. Because we know 1 doesn't work, right? So if p was bigger than 1, it would be blowing up even faster, right? because x to the p, where p is bigger than 1 and x is less than 0, is smaller than x. Yeah? So 1 over x to the p is bigger, so it's blowing up even faster. So if p is bigger than 1, no way will that work. Yeah? But if we take p between 0 and 1, let's see if that works. So let me try and put it over here somewhere. So 0 is less than p is less than 1. Okay? So what's the antiderivative of this thing? Then we're going to have 1 minus p over 1 minus p, right? If we differentiate this thing, we get this thing. Yeah? So let's factor out this. 1 minus p over here. And then this thing is just a to the 1 minus p. And the limit as this thing goes to 0 is just 1 over 1 minus p. Yeah? And since p is between 0 and 1, this is finite. This is finite. Yeah? So if we are just a little bit smaller than 1, we are not blowing up fast enough for it to be infinite, right? It is slow enough for that to be finite. So again, 1 over x is the cutoff, but now it goes in a different way. Yeah? Previously, if p was bigger than 1, then 1 over x as x tends to infinity is going down fast enough to be finite. Yeah? And now, as we do from 0 to 1, yeah, we have to have p between 0 and 1 in order for 1 over x to the p to be finite. It needs to not blow up too quickly. So that's our intuition we'll use to determine whether or not these vertical asymptotes will have finite area underneath. Okay, what about this? Suppose we have the integral from, say, 3 to 4 of 1 over, say, x minus 3 to the 1 over 3 dx. Let's try and draw a picture, right? So this is 3 to 4, right? Where do we have an issue with this? Where do we have an issue? Where do we have to pay attention? And then we'll have the bottom will be 0. So we have a vertical asymptote here at 3, right? A vertical asymptote at 3. And at 4, we have no problem. Everything's fine, yeah? So at 4, this is just equal to 1. So this thing is blowing up like this, right? So we're off the edge of the board, yeah? So we're going to have an issue here at 3, yeah? So to find this thing, we're going to have to just stop a little bit in front of it, right? And then find the area like this, yeah? And then we're going to have to take the limit as a goes to 3. That's how this thing will make sense, yeah? Cool. So let's do that calculation. So this thing, star, is equal to limit as x, or let's call it a, as a goes to, I keep doing that, a goes to 3, we're going to 3 from above, from the right-hand side, so put this right here, yeah? Of the integral from a to 4 of 1 over x minus 3 to the 1 over 3 dx. Yeah? Like this. So, what is this thing? Well, let's ask ourselves what antiderivative, let's put this better, there's 3. What do we differentiate to get this to x minus 3? If we try this, if we do x minus 3 to the 2 over 3, if we differentiate this, the power does indeed go down to minus a third, right? We differentiate the inner function, we just get 1, but we get this factor of 2 over 3. So if we do 3 over 2 like this, and we differentiate it, we do indeed get x minus 3 to the minus 1 over 3. Yeah, so this is the right antiderivative. Yeah, so star is equal to limit as a goes to 3 plus, and I'm going to have 4 to a of this thing right here, 3 over 2, x minus 3, 2 over 3. Yeah? And what's going to happen, we're going to pull out the 3 over 2. If we plug in 4, then we're going to get 4, well, this is 4 minus 1, so it's just 1, like this. And then as this thing tends down towards 3 plus, right, 3 from the positive side, then this guy here will just be some number very close to 3, a bit bigger than 3, minus 3 to some small power. So that thing will just tend to be 0, right? I can break up the steps and put that in as well, right? So that's equal to minus the limit as a goes to 3 plus of what happens when we put in this thing of a minus 3 over 2 over 3, right? And this thing is clearly going to be 0. So this answer will just be 3 over 2. Yeah? Okay, now look at the picture. Tell me why we would have anticipated this even before doing the calculation. How could we have guessed this before we did the calculation? How could we have guessed this before we did the calculation? Look at the power, right? We look how fast this thing is blowing up, right? Let me put the picture over here. So this is 3, this is 4. We have a vertical asymptote like this. How fast is this guy blowing up? So how fast is it blowing up? Tell me about it. Tell me about it, come on. How fast is it blowing up? Perfect, perfect, exactly. It's going up towards infinity with the power of a third, right? Yeah? In fact, morally speaking, in fact, more than morally speaking, all that is happening here is that we're just considering 1 over x to the 3 and we've shifted across to 3, right? Yeah. So the blow up here is exactly the blow up 1 over x to the 3 at 0, and we already worked out that that thing is finite. Yeah? Cool. So this is our answer, and our picture confirms it, right? And if I'd been more on the ball, I would have done the intuition before the calculation. Yeah? But at least we check our picture is consistent with our calculation. Yeah? Cool. Let's do just one more. Just one more. What about this? What about if we do the integral from 0 to pi over 2 of tan of x dx. So what does tan look like? Looks like this, right? Not doing this very well. Should go with slope 1. This is a bad graph of tan. This is tan of x, yeah? Because tan is equal to sine of x over cosine of x, yeah? And cosine at pi over 2 is 0, sine at pi over 2 is 1, right? So we're blowing up like this, yeah? Cool. And let's draw a graph of cosine. So cosine's doing this, all right? And here we are at pi over 2. Yeah? And then sine is doing this, so this is cosine. And this here, oh, different color. And this here is sine. Yeah, this is sine. All right. Tell me about the slope of cosine at pi over 2. What's the slope? What do you see on the graph? What's the slope?
It's negative.
Yeah, it's negative, right? And if we differentiate cosine, we get minus sine, right? And sine at pi over 2 is just 1, right? So the slope would be minus 1. So if I did the tangent line right here, it would be with a slope of minus 1. So it's not really good on my picture, but like this. Yeah? You see what I mean? Cool. All right. So let's look at this guy. Based on what I just talked about, tell me what you expect for this thing. What do you expect? Do you expect this integral to be finite or to be infinite? How is this blow up happening? Probably infinite. Tell me why. What's your guess as to how fast this is blowing up? How fast is cosine going to 0 as we're going down towards pi over 2? If we... As fast as the slope. Good. So if we had some number a here, right? Is there a way we could approximate how small this quantity is? What would it be roughly? How small would this quantity be here? So as a goes to pi over 2, it's decreasing, but can we get some estimate how it's decreasing? Look at the pictures. At the rate of the slope. At the rate of the slope. So what does the slope tell us about how small this thing is going as a tends towards pi over 2? What do you see here? What's the slope here? So what if instead of having just cosine, if we just had this slope? If we just had this tangent line? How quickly would this thing be going down to 0? What if we just had a function like this, where at pi over 2, it went down with a slope of minus 1, like this. And we considered this distance here, and we want to know how big this is. How big would this be here? No, nothing's so complicated. Just look at the picture. How small is this compared to this, if we have a slope of minus 1 here? Same. It's the same, right? You can just see it from the picture. It's the same. Yeah? So if this thing here is the number a, then this quantity is pi over 2 minus a, and this quantity here is also pi over 2 minus a. Yeah? Cool. And that's basically what we see here, because as we look closer and closer to pi over 2, cosine is more and more like its tangent line, right? Yeah, that's what we learned, right? So, for a, which is very close to pi over 2, then cosine of a is very much just like minus a minus pi over 2, like this. Yeah? In other words, pi over 2 minus a. I mean, we can just calculate the tangent line if you're not comfortable with this. Let's just do the tangent line. Okay? So the tangent line of cosine at this point, x is pi over 2, right? T of x is the slope, which is minus 1, x minus pi over 2, plus what happens when we put in cosine is pi over 2, right? That's the tangent line. Yeah? Cosine pi over 2 is 0, right? So it's 0. So it's this thing. So that's all I've done here. I've just used the tangent line. Yeah? But better is to look at the pictures. Better to look at the pictures. Cool. So we believe from this, yeah, that this stuff, cosine of a, right, is basically pi over 2 minus a. So when we consider sine of x over cosine, or actually call it a, because we just called it a, as a gets closer and closer, yeah, to pi over 2. How is this thing blowing up? Well, sine of a is tending towards 1, right? And this thing on the bottom is like pi over 2 minus a, for a tending towards pi over 2, this time from the left-hand side. Do you see what I mean? Okay, good. Now tell me more about why you believe this thing has got infinite area underneath its graph. Yeah. Perfect, because this is very much like 1 over x. It's blowing up like 1 over x, yeah? Yeah? Cool. So, this might have been a bit complicated because you're not used to this. But this is one of the things I'm going to try and teach you. You're going to look at pictures. All we did here was describe pictures. We described pictures. Yeah? We looked at the picture of sine. We looked at the picture of cosine. Yeah? And we looked at the slope, and we saw how quickly cosine was tending towards 0 as a tends towards pi over 2. Yeah? And we see it tends towards 0 basically like this, like pi over 2 minus a. So this gap is the same as this gap. Yeah? All this is the description of this picture right here, that this gap is the same as this gap. Yeah? So when you get used to doing this kind of stuff, you will look at pictures, and you'll only need to do this stuff to clarify what the pictures tell you. Yeah? So looking at pictures for you, this gap is like this gap, so 1 over cosine is more and more like just 1 over x when we are approaching pi over 2 in terms of its growth, in terms of its blow up. Yeah? So for that reason, we expect this thing to be infinite. We expect this thing to be infinite. And if we do a calculation and it's finite, we think something's wrong. Okay. Now that we have what we expect the answer to be, we can do the calculation. All right, let's do the calculation. So what is this? This is the limit as a tends to pi over 2 from the left-hand side now, because we have to approach it like this, right? From 0 to a of tan of x. Yeah? What is the antiderivative of tan of x? This is the limit as a tends to infinity log absolute value of secant of x. This is something you won't be expected to know. If you're asked a question like this, this standard antiderivative will be given to you. Okay. And then what is this? This is the limit as a tends to 2 of log absolute value of secant of a should have done a big clean off before I started. Minus log of secant of 0, which is just log of 1, which is just 0. So let's just not bother with that. So it's just this thing. It's just this thing. Yeah? And then what is this? Well, this is a composition of two functions. Secant is 1 over cosine, right? As we approach pi over 2, as we've just learned, since cosine is tending towards 0, as we approach pi over 2, secant is tending towards infinity. Yeah? So this stuff here is tending towards infinity, and we're applying log to it, right? So this thing is definitely going to infinity. Yeah? That's composition of continuous functions. This is what you learned from last semester. Yeah? So as a gets more and more close to pi over 2, this thing, secant, is bigger and bigger and bigger, and we apply log to it, and it's still getting bigger. Yeah? So this is indeed equal to infinity. So the calculation confirms what our picture says. Yeah? And even better, if you didn't know what the antiderivative of tan was, you could still figure out the answer from this kind of thing. Yeah? If this was a free response question and you argued like this, I would get you full points. I'd be, in fact, much happier if you did something like this than if you did a calculation, because it shows that you see what is happening. Okay? All right, so, sorry, this went on longer than I intended, but this is the kind of thing I'm gonna emphasize going forward. So now we're more and more out of the algorithmic part. I'm gonna try and teach you to turn stuff into pictures and figure out your answer from pictures in this way. And if you get into doing this, you'll have an enormous advantage. This is actually what this stuff is. This is a language that describes pictures that we see in our heads. Well, amongst other things, it's a language. So the faster you get into turning the language into the pictures and understanding what's happening there, the better and the easier this thing will be for you, and the more meaningful it will be going forward. So for some of you, this is new. It might seem harder, more complicated. That's because it's new. If you learn this, if you get into this, it will put rocket fuel in your understanding of math, of calculus, and all further math. Take my word for this. Trust me on this. This is one of the main things I can teach you in this semester, is we're going to turn stuff into pictures, and we're going to understand it from the pictures. So if this wasn't clear to you, spend a bit of time with it, and all further explanations I give in terms of pictures, make sure they sink in deeply. And you will find that this whole thing will be a lot clearer to you. So just trust me on this. All right. Thank you for your patience. Have a good rest of your day, and I will see you all on Friday. Bye-bye.